So it's my pleasure to introduce Professor Nils Andersson to give today's webinar. Many of our talks are focused on quantum fluids, superfluid dynamics within the lab, or theory that's focused on the lab. Today we'll consider quantum fluids and superfluid dynamics in the wild, as it were. And Nils will tell us about the superfluid dynamics of neutron stars. So please, when you're ready, Nils, take it away.
Okay, so thank you, Andrew. First of all, for those of you who know me, you'll recognize that this is not my usual voice. So I have an apology to make. Actually, I've got two. So the first apology is that I sound like this because I had an unexpected operation on my neck a couple of weeks ago. And so I'm kind of recovering now. And everything is fine apart from the voice. So I have to start to do these things that, you know, the classic Stephen Hawking thing where you have to start by saying, "Can you hear me?" Of course, he did that with a computer voice, and I'm almost there. So we'll see how that works. Hopefully you can hear me. If you can't, just shout. I can't do anything about it. So there you go. Anyway, the second apology is that this is not exactly the talk that I planned to give when Andrew first asked me. Partly, again, because of this operation, I didn't have time to put something that was much newer together, but that's fine, I suppose. And so this is more a review. But as it turns out, and this is not an apology, it suits very well to give this talk right now because very, very recently, a good friend of mine passed away. And so, let's see if I can actually change slides, which I apparently can't. There, up, there. So a couple of weeks ago, those of us that work on neutron-star superfluids lost a great pioneer and champion of our area, Pierre Pizzuchero, who worked on a number of things to do with neutron stars and superfluids and especially pulsar glitches. So I'd like to kind of give this talk in his memory, and I'll point to some of the things that he did as I go through the whole thing. So I think that kind of works very nicely, and it feels good for me to have an opportunity to do that. Okay, so to get started, for those of you that don't tend to think about these things, neutron stars is pretty much the playground where all of physics comes together. So a neutron star is born when a normal star dies in a supernova explosion. The core collapses down to something like 10 kilometers. So the mass, a little bit more than the sun, is compressed into a radius of about 10 kilometers. That means you got extreme density. You have initially extremely high temperatures, like 10 to the 10 Kelvin. And basically, this means you take all the physics you can think of, extreme density, so high supranuclear density, some very strong magnetic fields, high temperature to start with, and so on, mix it all together, stir it for a bit, and then try to understand what's going on. Now, the key point for today is that even though these stars are born very hot, 10 to the 10 Kelvin is really quite puny if you calculate temperatures for nuclear physics. So the typical temperature scale for nuclear physics is 10 to the 12 Kelvin, the Fermi temperatures for the nucleons, the neutrons and protons. And so we expect that in this predominantly neutron-based star, the neutrons are going to be superfluid. Similarly, there's going to be some protons because of the strong interaction is kind of necessary, and these are going to be most likely superconducting. And so we're going to have, if these objects rotate or slosh about, we're going to have superfluid vortices, just like in helium. We're going to have superconducting flux tubes, just like in superconductors. Of course, it's a little bit worse than the lab systems, because I'm going to have a mixture of superfluids and superconductors. And even worse, as I go towards much higher densities, the nature of the physics might change. I might have things like deconfined quarks, so I can have quark superfluids or color superconductors. All sorts of things can happen. And then if I really wanted to do this, I have to model this in the framework of Einstein's general relativity. So I need relativistic gravity. So there's quite a lot here. I'm not going to talk about most of this. What I'm going to focus on is what we think we know about superfluidity, in particular in neutron stars, and why we think what we think, and how we may be able to, or think we're able to some extent, constrain the nuclear physics parameters. So that's the scope. Okay, so looking then at superfluidity, I mean, first of all, we all know basic textbook physics. You take matter and you cool it down. There are two choices. Either you get a solid or a superfluid. So in a neutron star, in the outer region, out to something called neutron drip, or beyond something called neutron drip, but whilst the nuclei still form sort of an elastic lattice with increasingly neutron-rich atoms, we also have a superfluid gas. So we have a mixture of an elastic lattice and a superfluid neutron gas. If you go a little bit further in, this lattice becomes unstable, and we basically have superfluid neutrons mixed with a few protons, which are likely to be superconducting. So what I'm showing in this sketch, and it is a sketch because, frankly, we're not very good. I'm saying we are not, I'm not good at all, but even the people that are good at this are not exactly sure about the pairing properties of neutrons and protons, especially not when you have some mixture of the other guys present. So if you have only neutrons, it's calculable, but if you have neutrons and some protons, then it's a little bit harder. So we're pretty well, do we think we understand the singlet pairings, what happens at low densities into the star's core, which is this faint vertical dashed line. So in the lattice of the crust, we think we know roughly what's going on, and the critical temperature for superfluidity is something like 10 to the 10 Kelvin. So typical neutron star cools to this temperature in a matter of minutes to hours. Then we have the core, where the story is much less certain. We have triplet pairing of neutrons, the red curve. That temperature is likely to be much lower. In fact, it might be absence altogether. So there might not be superfluid neutrons if we go to very high densities. There will be superconducting protons. The problem there is if they form a type 2 or a type 1 superconductor, or in fact, some kind of mixture. That's a little bit under debate. So this story is a bit complicated, and I could make it messy by going to even higher densities and putting other stuff on here, but I don't want to do that. So the simple point is, we've known since the 50s, from basically applying BCS theory to the nuclear physics here, that we're going to have pairing gaps for neutrons and protons that look a little bit like this. We have some observational evidence, mainly from what we call radio pulsar glitches. So these are events where radio pulsars, who are very, very stable clocks, typically spinning down gradually, every now and then just seem to rapidly spin up and then relax. So we've seen these glitches in over 100 systems. Some stars glitch very regularly. I'm going to show you a couple later on. Some we've only seen the glitch once. We don't really know why, apart from the spin down rate has got something to do with it. Now, the standard idea is that this is smoking gun evidence for superfluidity in these systems. So it's a simple story, and I'll show it to you in a second, but the truth is the calculations are hard. So one reason why it's hard is the story is simple, but the phenomenology of the observations is quite complicated. So we think we know roughly what's going on, but it's like at the cartoon level, and we'd like to do better. Okay, so here's the story. The standard picture is, we know we have a crustal lattice and a superfluid together. It's a rotating body, so the superfluid should have vortices. But the vortices might not move easily through this nuclear lattice. And so if they're pinned, we could prevent the superfluid from spinning down. And so in this cartoon of just showing the crust spins down due to electromagnetic braking, the blue curve, the superfluid vortices are pinned, so it doesn't spin down until something magic happens. And then the vortices become free to move, they unpin, and so the system relaxes due to friction, again, like in lab systems. And so the vortices catch up with the crust, they move out, the spins rates relax, and then basically the system resets again, vortices repin, and you can go again. So this is a natural kind of explanation based on what we see in the lab, but we'll see later that it might not be entirely that simple. So this is the first place where my friend Pierre did a lot of work. He was one of the world's experts in the pinning interaction to cross nuclei. Questions like, if in a nuclear lattice at different nuclear densities, neutron vortices pin to the nuclei or in between. And the truth is, we think that it depends on where in the crust you sit. So in some parts of the low density region, vortices pin to nuclei. If you go deeper, they pin to the in-between regions and so on. So it's quite complicated. But Pierre did some of the best calculations, I think, of what this pinning potential looks like. And so I'm going to talk a little bit about those results in a minute. So the story then is the neutron star, which we observe the electromagnetic field basically through the pulsar mechanism, spins down due to electromagnetic braking. Superfluid only spins down if vortices move. They can't if they're pinned. Superfluid lags behind. And so at some point, we don't know why, the vortices or a large number of vortices are released, coupled to the crust, and then we see the star spinning up, reset, go again. So that's the explanation. It has been the explanation since about 1970. It's still the explanation, and I could finish the talk right here because this is pretty much what we know. Of course, I'm not going to stop right here. So there you go. So here's a couple more pictures. The top is from Danai Antonopoulou in a study of a number of glitches, where it highlights a few other things. The star spinning down is the initial step in the spin down rate, and then an exponential relaxation that follows typically a very fast recovery. And then in many systems, in some systems at least, we also see a persistent change in the spin down rate after the system, suggesting that maybe this reservoir of superfluidity and vortices doesn't quite reset to where it started out. So the story is a little bit more complicated than the cartoon. Now, much of this is just then in the observations matched to exponential recoveries and so on. We know the timescales are days to months, much longer than what we can explain with neutron star viscosities. So you need something that allows viscosity to go out of the picture, and superfluidity is the obvious candidate. At the bottom, I'm showing a few examples of why the story is a little bit more complicated. So this is from work by Cristobal Espinosa, one of the great experts who did his PhD at Jodrell Bank at Manchester on pulsar glitch timing. And you can see top panels in each case shows the change in the spin rate. And you see that they're a little bit different. You have a step and then slightly varying behavior. The bottom panel shows the behavior in the spin down rate. Again, the glitch itself, the step, is easy to recognize. The relaxation is clearly not identical in each case. And you can see why I prefer to think of our theory as a cartoon rather than a sort of model. Okay. So now you have a choice. You can either try to look at the whole sample of all the glitches and extract statistical properties, right? Then ask, on the whole, how does this system behave? We've seen glitches in 100 pulsars, maybe some of them, maybe dozens, some of them just a few. Adding all this up, we've got a few hundred events, so we can do statistics. Not great statistics, but we can do statistics. Or you can do what I prefer to do, pick your favorite system, ideally one that has shown several glitches, and see if you can beat that one with theory. So can you explain at least one system? If you can't even do that, then maybe you're not doing well at all. So you pick the simplest, the one that behaves the most regular and so on, and see what you can do. So one of those systems is the Vela pulsar that we've seen glitching since the 70s. And I'm going to show you some results for that. But before I do that, I wanted to highlight a slight difference between the lab systems. So the idea here is very much based on the two-fluid model for helium-4. But the motivation we tend to use is a little bit different. And I thought it would be interesting for you guys to hear how we think about this. So you all know, right, for helium, that the classic model separates a normal fluid component with some density, I've called it rho n, from a superfluid with density, say, rho s. Now, these two quantities, we all know you can't measure either of these, right? Because at all the atoms are paired, these guys only have statistical meaning in a sense, right? You can't say this particular helium atom is superfluid and this one is not. So that says basically this is separation into 2 degrees of freedom. And there are other ways of doing this. So the way I'm going to be doing is slightly different. And that is to say, I'm going to take all the atoms and put them in a box over here. That then has a mass density that I can measure, I can weigh it. And it has some velocity I can measure from the mass flux. And then I take all the thermal excitations, which clearly can't exist separate from the fluid, from the atoms, but that doesn't matter. And I'm going to represent that with a massless entropy. And then I'm going to be a real heretic. I'm going to think of this entropy as a fluid. So I'm going to come back in a second to why that is a really smart move. At least I think so. So then what I can do is I can relate these two, and I've written down the relation down here. Basically, on the left, I've got rho times Vn, little vn. That's the mass flux, which is kind of measurable. And then I have the total density, the rho. I've got the Vs and the Vn, the superfluid velocity, the normal fluid velocity that we normally talk about in the classic model. And then I have a parameter called epsilon. Now, this epsilon comes from the other way of describing this, and it's basically a measure of how easy it is for the thermal excitations to flow or drift relative to the atoms. We call that entrainment. It basically says to what extent the heat is forced to move with the atoms. Now, the way I've written this, you can see that if I want to go back to a system that has, and you can go back to the next step, I've written down what the densities, the superfluid density and the normal fluid density in the standard picture would be in this language encoded in this entrainment parameter. So I'm basically replacing those two densities with a total density and this entrainment parameter. And now if you're a bit clever, you'll see that if I want to go to a system that is non-superfluid, so I want the superfluid density to vanish, then I need this epsilon, the entrainment parameter, to diverge. So that might not be very pleasant or seem very pleasant, but actually it's just a picture of saying that as I go to the superfluid transition, I have to lock the two components together. And so this epsilon diverges, and that forces the two velocities to become the same. So this is just a slightly different picture. So I prefer this way of thinking about it for 2 reasons, 3 reasons really. One, I want to be a bit different. It's a really bad motivation. 2, this lends itself a little bit better to the neutron-star picture, where we've got neutrons and protons and thermal excitations. In that system, it doesn't make sense to start talking about superfluid and normal fluid neutrons, superfluid and normal fluid protons. So it's kind of easier to think about all the thermal garbage, if you like, all the entropy as one object. That's a little bit simpler. Secondly, or thirdly, it turns out that this entropy entrainment that I put into this model allows me to describe how heat in lattices, so in lab systems that are not superfluid, can go from basically wave motion described by a Cataneo type equation through to diffusion. And that allows me to go into relativity and explain, again through this entrainment, why there is a thermal relaxation that says that a relativistic heat is not described by a diffusion equation, but in fact by a wave. So that is the motivation for why we do things a little bit differently. So on to neutron stars then. The very simplest model from the get-go says that electromagnetism or magnetohydrodynamics is far too difficult for any human beings to deal with. And so we're going to get rid of it by assuming that we can couple all the charged particles. So in my models, typically electrons and muons coupled to the protons on short timescales, so I can ignore the magnetic field. Now, clearly, that's a cheat, right? Neutron stars have magnetic fields, so I can't do this. But for the purposes of the fluid dynamics, I'm going to do it anyway. But then, because I want to work with a fluid model, I have a 10-kilometer ball, right? I don't have the luxury to think about, smaller scale systems. I have to work with fluids. So I need to average over vortices and flux tubes. So clearly, they have to be dense enough that I can do this. And in neutron stars, they safely are for all systems of interest, okay? And then I need this entrainment that now is due to the strong interaction and tells me to what extent protons are forced to be dragged along with neutrons if the neutrons move and vice versa. And so that reduces the superfluid system to a two-fluid model. Now, motivation is very different to the lab system, but the phenomenology should be the same. There are vortices that couple the two through mutual friction. That's pretty much it. Okay, so the equations look a bit like this. I've got two entrained interacting fluids. I'm labeling them by X. So X could be for neutrons, N, or P for protons. I've got two mass continuity equations, just look like the usual single fluid thing. Two velocities Vx, two number densities Nx. I've got two coupled Euler equations, and these look quite different, okay? So let's unpack what I've got here. So first I've got, for the X fluid, say the neutrons, I've got the usual convective time derivative. So the derivative moving along with that fluid. I've got the momentum, which I call P. I'm going to come back to that in a minute. I've got the gradient of the gravitational potential, because my star has gravity, right? I've got the gradient of the chemical potential of this fluid. So that's quite standard. And then I've got this odd-looking term that involves this epsilon, the entrainment, involves the relative velocity, which I call W, between the Vy, so the one that's not M, P then, and the fluid, and then basically the shear of the fluid, or the velocity. And then I can have extra forces on the right. They could be viscosity, they can be the mutual friction later. So the momentum involves this entrainment parameter. So basically now, in this expression for the px, you see what the entrainment does. It basically says the momentum of the fluid is not proportional to the velocity. It involves also the flow, the velocity of the other component. And that allows the momenta to be misaligned with the vortices, or allows me to describe to what extent the other guys are dragged along if the first guys move. Okay? So one way of thinking about this is to think of the entrainment as an effective mass. So I've just written that down for the protons down here, where I've written an MP star. MP is the bare free mass, if you say, without entrainment, and NP star is the entrained mass, the effective mass, and the epsilon P then just says, okay, this encodes how heavy the protons feel, because if they move, they drag some neutrons along with them. And typically, this effective mass is quite close to the bare mass, so this entrainment parameter is small. But it doesn't have to be so. In fact, we've learned over the last decade or so that the effective neutron mass might be very large in the lattice of the neutron star crust. So that's due to a completely different mechanism, effectively Bragg scattering of the neutrons off of the lattice of nuclei. So that's a very complicated problem. We don't know for sure that the entrainment is as large as I'm going to be assuming the following, but it could be. There are several calculations suggesting that it is. Okay, so here is the Vela pulsar. At the top, one of the most enigmatic systems we have. It is my favorite, maybe, or maybe not quite my favorite, but it's one of my favorites. It's my favorite because, as a theorist, I'd like to be able to describe what's going on. That's my job, I suppose. And so if I look at this B083345 phone number, I can sort of pretend, at least a little bit, that I can take one of these glitch events, the sharp steps and the relaxation after, cut and paste, slide it along to the next one, and it almost fits, okay? So I can sort of convince myself, at least by squinting, that the same thing happens over and over and over again. And that fits my cartoon understanding of what a pulsar glitch should be. So then I can go and say, can I explain this? And the answer is, well, actually, not so much, but I can explain some aspects of it. And at the bottom, we have another example, and you can see, in this case, a couple of this is a system that hasn't glitched as much. We haven't observed it for long enough. And here you see several glitches. The behavior is clearly not as regular. This guy would be much more difficult, or at least more difficult. Okay, so one thing we can do is say, okay, suppose the cartoon picture is true, right? Suppose we have a superfluid reservoir, and suppose we relax all the vortices in each glitch, right? So the all vortices are pinned, all vortices are relaxed, and so then I can basically work out what is the moment of inertia in this superfluid, right? And then I can compare that to the size, the magnitude of these glitches, and I can get a number out. So this is what I've done in the panel at the bottom. This takes the accumulated change in spin. The units don't mean anything. In terms of modified Julian date on the horizontal, I just stack them up. And then I've squinted at that and said, look, I can draw a straight line. Because if there's one thing I'm really good at, is straight lines, right? So I draw this straight red line, and that allows me to work out the moment of inertia of the superfluid. And the number here comes out to be about 2% of the total moment of inertia. And that's a nice number, because that's the number that I get if I go back to the very beginning. I'm going to do that to be difficult. So all the way here, and I take this big red pairing gap and work out what the moment of inertia is of that pairing in the neutron-star crust. It's about 2%. So I'm done, right? I've explained this. I can stop the talk right there. So it works as long as I ignore the entrainment. And so the problem is, if I account for this Bragg scattering entrainment in the neutron-star crust, I lower the moment of inertia effectively by a factor of something like 5, or at least a few. Now I don't have enough to explain what's going on. So this is difficult because that says the superfluid in the crust is not enough to explain the glitches. So I have to go into the neutron-star core. And that's difficult because, as I showed in that cartoon of the pairing gaps, in the core, I could have a much larger region of superfluidity, so a much larger moment of inertia. And so then I can't explain why I should only have a part of that involved in each glitch. So why would the glitches be the same size? Why can't some of them be real whoppers, so absolutely enormous, and some of them be tiny? I don't know. So I need some explanation as to why only a fraction is involved. Assuming that only the crust does the job works, but the numbers don't work out, so I need more. So why not? So one explanation could be that I only have the singlet pairing. I don't have the other superfluid region. And the singlet pairing gap is such that it just reaches a little bit into the core, just enough to explain the observations. And then I'm done again. So that could work. And before I tell you about the implications of that, let's just admit the reality. It could also be that I'm just not good enough at calculating. Maybe my theory is not good enough. The superfluid parameters could be wrong. Maybe this entrainment in the crust is not as big as we think. Maybe the pairing gaps are slightly different. So we need to do better. But the cool thing here, and this is another piece of work that Pierre Pizzacchero did quite some work on. Pierre did quite a lot of work on, so I'm using a figure from one of his papers. So the cool thing is, if I take explanation number 2, right? Then I have a statement that if I understand the superfluid pairing, I will know what the superfluid moment of inertia is exactly. I will know how big the glitches can get exactly. And then by measuring either the accumulated glitches or the largest observed glitch for any given system, I can say for some given matter description, some given equation of state, how heavy the star is. I have an internal weighing scale, and this would be completely unique in astrophysics. When we weigh stars, we only ever do it by having them in binary systems. But superfluidity could allow us to work out the mass of a star, a single star, without a companion. I think that's really fascinating. So the figure shows the results of one of Pierre and his collaborators, how he's taken some neutron-star equations of state, SCER model, BSK models, doesn't matter, taken the largest glitches observed for a bunch of pulsars, and then said, well, for these different matter equations of state and some pairing gaps, the masses have to lie to the left of these curves. The stars cannot be heavier than this. And so it's an upper mass limit on these systems. And that is kind of cool. So now you could imagine testing this. If we had one of these pulsars in a binary system, so we could work out the mass independently, then we can run the story backwards and put constraints on the superfluid parameters. Maybe that's the way this is going to go in the future with the square kilometer array. But anyway, I think it's a really neat story. So a little bit on to the other parameters, the mutual friction. So the mutual friction looks exactly like in helium because we've stolen, Joe Vinan's and Henry Hall's model. That's the truth of that. The Magnus force is exactly the same, and so on. The vortex mutual friction is motivated. Mathematically, it's the same way. Physically, the parameters are a little bit motivated a little bit differently. Again, they come from entrainment, and they come from the fact that if I have a flow along my fat flux tube that I've sketched here, the red could be neutrons, the red arrows going around. They drag some protons around with them due to entrainment. The blue one, that magnetizes the vortex, and now it can interact with the electrons in the system. So this is a model proposed by Jim Sauls and others in the 1980s, and that's the standard model for neutron-star mutual friction. So mathematically, looks like what you're used to. The only difference is we quantize the omega here is the quantized vorticity that also had the entrainment in it. But other than that, this looks just like helium. And just like in helium, the typical mutual friction parameter, the R here, is small. And the electron scattering system that I suggested also leads to a small value of this parameter. But this could also be different. If I have vortex flux tube interactions, then basically that becomes an electromagnetic interaction. The magnetized vortices try to cross through superconducting flux tubes. That could be costly. And so that could be a much stronger effect, much harder to model because it's velocity dependent. We don't really know how that works, but some people are working on it, and every now and then when they fancy, I suppose. Certainly work to be done. So here is some example of how we can put constraints on mutual friction. So the idea now is that in the cartoon explanation of the glitches, mutual friction tells us how rapidly the system couples. So that is basically how sharp is this step that we saw in the plots. Okay. Now that's very, very difficult to resolve. You have to be very lucky. You have to have a radio telescope pointing at that precise pulsar at the moment when it glitches. So that's not going to happen typically. But due to an absolutely spectacular observation led by Jim Palfreyman in 2016, we know that this glitch rise has to happen on a timescale faster than something like 40 seconds, maybe 10 seconds, right? And so that means I can put some constraints on the mutual friction. So I can test the theory calculations. And so here is the bottom right is a plot from work by my student Vanessa Graber, again a few years ago, where she's taken the standard model of mutual friction that I showed you, the usual one, and she's modeled effectively it's a R parameter, which is called B here, and she's showing that the number that fits quite well, the red is the data points from this Vela glitch. You can see that the relaxation here kind of aligns up sort of with this purple line, the solid line, which is a number of, I think, about 5 times 10 to the minus 5. We think from theory calculations, this number should be ballpark 10 to the minus 4. So this seems to fit our understanding pretty well. Of course, this is one system, one object, one calculation. We really need more data. And again, I hope this will come with a square kilometer array because then one should be able to monitor many more pulsars much more regularly, and we should have an abundance of glitch data. Okay, so that's all I think I'm going to say about glitches, apart from where we stand with modeling this. So basically, we have the cartoon explanation. We need to do better. So there are 2 stories as to why the glitches happen. One, again, is due to Pierre Pizzucchero. It's called the snowplow model. It basically says this pinning potential that Pierre calculated peaks at some density, at some radius in the star. And the idea is that the vortices bunch up at this peak of the potential, and then they all decide to go and unpin at the same time at this peak. So a little bit like a snowplow pushes snow and then suddenly it just breaks free. Another model is due to our group, work by Kostas Klampidakis in particular, and that is that as you build up the relative flow between the components, you build up velocity lag, and then you might trigger 2-stream instabilities. So basically an instability because you got a relative flow in the system. These things are common in plasmas, and so we've shown that these things can happen for superfluids as well, for neutron-star superfluids as well. And then there's other work that focuses, as I said, more on the statistics. That work looks at a bunch of glitches showing that these can be thought of as avalanches. So this work mostly by Andrew Milotas' group in Melbourne have scale-independent behavior and so on, looking a little bit like earthquakes. Now, can we do the calculation of the vortex dynamics? Well, in a sense, maybe yes. So here's a little movie that's tantalizing, I suppose, from my former student, Bryn Haskell in Warsaw. So what he's doing a Gross-Pitayevsky 2D simulation of vortex behavior with friction. Standard kind of calculation for lab systems. And what he's seeing is that if you put a little cross layer in the outer region, this cross layer is seen to spin up every now and then as the star spins down or the system spins down, gross properties, but as the vortices go, when you see these little blue cascades, you get these little glitch-like things. So this is quite nice. This looks like a system with glitches, right? But a tiny one. So, job done. Apart from, I don't think so. Because remember, in the beginning, I said we have to average to get a fluid model. And when I average, I have to average over the vortices. And if I average over vortices, how many do I need to average over? 100? 1,000? Well, let's say 100. Well, how many do I have in this simulation? 100. So the point is, I might actually only here be looking at single fluid elements. I still have to do the averaging over them to get the hydro, right? So the large scale hydro. And so the story here is I need to figure out how to average from the coherence length, about 100 Fermi something, give or take, up to 10 kilometers. So, you know, there's a few orders of magnitude missing. And if you put in the context of numerical simulations in in relativity, the best we can do for neutron stars are simulations of maybe 10-meter resolution. And so there's no way that I can go beyond that, at least not in the foreseeable future. So I need a model that tells me what happens on the 10-meter scale, and we're clearly not there. So this raises, I think, one of the main questions for our problem, which is how do you average or filter the small scale features up to the scales that we can simulate? And of course, that's a standard classic problem in fluid dynamics. Some questions involving classic turbulence and so on. And so I think, and that's what I wanted to talk about, but then I had my operation, I ran out of time. And so what we need to do, certainly for the neutron star problem, is figure out how do we apply some version of the standard or some version of the filtering averaging that people use for classic fluid turbulence to quantum systems with quantized vortices, in our case, the two fluid components. There are some really nice conceptual questions to go with that. And I think if we can figure it out, we might also be able to make statements about things like polarized turbulence that we see in helium, where we know, I think we know, that it's not just a question of adding the turbulent mutual friction to the normal sort of aligned vortex mutual friction. It's a little bit more different. It's a little bit more complicated than that. And maybe this kind of filtering story can explain that. Okay, so I'm running near the end. I wanted to just point out one other thing. It's got nothing to do with superfluidity, but it's really cool. So here is another pulsar that glitches very regularly. It's a young pulsar called 0537 in the Large Magellanic Cloud. So it's a fairly young object that spins at 16 milliseconds. So you can see it glitches roughly every 100 days. And it's extremely regular. And again, it looks a little bit like the Vela pulsar case, where I can take some of these and overlay them on each other, and they look similar. So the interesting thing with this is I can measure, again, the moment of inertia. The story is the same as before, so I don't need to talk about it. But there's one extra spin to this system. The glitches are regular, and I can pretty much predict the size of each glitch with a waiting time to the next one. So that's in the little panel up on the right. So you can predict how big, how long is it going to be? If a glitch of a certain magnitude happens, how long do I have to wait? And so that fits this cartoon, that I have a certain reservoir and I relax some of it, not all necessarily. So that's nice. The other thing which is nice for me as a gravity person is that we spotted when we worked on these glitches that the breaking index, so the second derivative of the spin, change in the spin, for the largest events seem to asymptote to a very peculiar value of 7. And that's basically one data point, and the plot down on the left, it's got quite big error bars, so it's 1 point that sits roughly at 7. And if you squint and draw a curve that I've drawn by hand, you can maybe convince yourself that the whole accumulation of events asymptote towards this 7. So why is that interesting? Well, 7 for a gravity person as breaking index of a neutron star is interesting because it is the predicted value for spin down due to gravitational wave emission associated with unstable oscillations in the star. So these are called Rossby waves or R modes. And this 7 came out of nowhere and has, in fact, stimulated the LIGO collaboration to look for gravitational waves from this pulsar, obviously finding nothing, but otherwise I would talk about it. But the nice thing here is this idea is a little bit out there, but it is something that will be testable, I think, with future gravitational wave instruments. So it's a completely different part of this story, neutron-star seismology, which also has, interestingly, superfluid aspects where you can look at to what extent the superfluid impacts on the tides raised in the neutron-star binary. But I'm going to leave that for another talk because I'm close to the end. So, to summarize, I've talked about glitches. We've observed glitches for more than 50 years. We've made progress, but maybe not as much as one would have liked or maybe expected. The problem is hard. We think we know. We need superfluidity, superconductivity. We need vortices. That's sort of a no-brainer. Superfluidity in neutron stars is important for many other things. Cooling after X-ray bursts may explain free precession or absence of. Seismology, as I said, gravitational waves. The magnetic field evolution in neutron stars is strongly linked to whether the system is superconducting or not. So this is a much bigger story with a lot of other aspects. I ignored the magnetic field. Clearly, you can't do that. We don't have clear answers to the what, why, how of glitches, but there have been interesting results, and I hope you agree that it is an interesting story. What we've learned is, for us, the entrainment due to strong interaction between neutrons and protons, or due to interaction with the lattice nuclei in the neutron star crust, is important. It also dictates the mutual friction damping. We've learned that we should do more work on the various instabilities, what triggers turbulence. That story, I think, is the same for lab, or similar for lab systems, and there's a lot more work I think we can do. We've learned that the pinning is really important. The work by my friend Pierre, who passed away, has been extremely valuable. I hope someone young comes along and picks up the mantle and runs with that, because we need to do better on that problem also. The main thing, I think, and the take-home message is, I need a fluid model that can operate on the scale that I can simulate, 10 meters, 100 meters. I don't have it. So I need to make the model more sophisticated, and I need to make it workable. And I think on that, I'll leave it. Thank you.
Thanks very much, Niels, for a very interesting talk, and the gauntlet has been laid down. So, any questions, either feel free just to unmute yourself, or if your connection's a bit shaky, pop it in the chat and I can read it out. While we're waiting for people, I just wondered, you ignored the magnetic field and acknowledged that. I wondered if there was a cartoon picture, at least, for what that might do.
Yeah, so the cartoon picture would be nothing, right?
Okay.
But the story could be more complicated. If in the star's core I have superconducting flux tubes, and if there are vortices and the vortices want to move, they can push the flux tubes out, okay? And so that could impact on field evolution. So that's a problem where, again, we have a cartoon story, but we don't have calculations that can do it. I think one of the few people that can do this is probably you, because you know how to simulate magnetized sort of flux tube things. So you need a mixture of two, and you need to look at how they interact. So I think we talked about this years and years ago.
Yes, yeah.
And it's hard, right? It's hard.
There may be some movement on that on that front in the future. Anyway, let's not make it too self-indulgent. So Luca has his hand raised. Please, Luca, when you...
Yes. Thanks for your very nice talk. My question is it possible to calculate the condensate fraction of neutron matter in these neutron stars?
Okay, so what you're asking about really is, can you add temperature effects, right?
Well, I'm not speaking about superfluid fraction, but the condensate fraction. Yes, that is a bit different.
No, I think in my picture, the answer is no, it's not different. But we can discuss that.
Okay.
Okay, because if you think neutrons, all the neutrons are bad, right? And so they're all part of the superfluid in a sense, right? But if I add temperature, then there are also the excitations. So then I can start thinking about a condensate fraction in the way of thinking about it. And so I can try and do that. People have done a little bit of work on this. The reason we don't tend to do it is it just makes life really difficult. So there is work on it. There's been some work on temperature effects, especially how it impacts on this entrainment. So you can measure it through this entrainment parameter. But there has nowhere near enough work on this. But yes, it is calculable, but we haven't done enough work on it.
Okay, thank you. Thank you.
Samuli, you are next.
Yes, thank you for a very nice talk. First of all, I will steal a few seconds and say that there are many people here today who maybe don't join regularly. So if you'd like to be added to the email list, please send me an email or a private message on the chat here. And then my question was, a few years ago, we did helium-3 experiments in the polar phase of superfluid helium-3, which you stabilize by putting helium-3 within a certain aerogel. And we studied vortex dynamics in that system, which is basically, well, there is no dynamics until an avalanche of vortices changes the configuration. So vortices are pinned and then it rapidly changes and then it's stuck again. And I was going to ask you, if we had an experimental platform like this, would you have any kind of questions in mind for an experimentalist in our field, or what to look for that might be useful for your neutron-star perspective?
I think that's an excellent question. It reminds me of a conversation with Jim Sauls some years ago, where he was very keen on aerogels and those as a system. I think the answer is probably yes. I'd need to think about it a little bit. But then the question is also, no, in short, the question is yes, right? So let me get back to you on that. I think it's a very, very nice development. And I remember reading some of these papers when you did some of the experiments. I don't fully understand, just you're asking me the question. I would ask you lots of questions too. So we should arrange to have a conversation.
Yes, let's do that.
Absolutely. So there is a question from Mark in the chat. And so the superfluidity does change character at the boundary. Now, there is the question, what happens to vortices? I think it's a general question for vortex dynamics, right? If you go from one phase to another, what the vortices do. And so I think, I don't really know. I think we do need to do more work on that, certainly for the neutron-star problem, right? But I think that, so either, of course, one option would be, if you want to cop out for how you can explain how the only, say, the singlet pairing vortices take part in the glitch. If you have triplet pairing vortices are allowed to slide, right, at an interface, like, some surface there, you can allow currents, then you can be back in business explaining things with a singlet. But I don't know. I think that's above my pay grade at the moment. So thanks, Luca, for putting that paper in the chat. I'll look at it.
You're welcome.
So we have time for one more question.
Hi, Nils. May I ask you a question?
Yes, of course.
Hi. I'm a bit puzzled about just this slide here. So you suggesting that glitches are triggering R modes, or
yes, that's exactly the story. That and we look. To be honest, I don't believe this for a second, right? But we looked at the glitch relaxation for this particular pulsar. And extracted from the data this number 7. And we know that the number 7 shows up in the story of the R-mode oscillations and gravitational waves. And we're not stupid, or we might be a little bit stupid, but not that stupid. So we knew that other people working on this pulsar, they would spot this 7, and they were going to write this paper. So we did. So I don't think this relaxation of breaking index 7 is perhaps real, but it could be. And the point is, it is testable, because with the next generation gravitational wave instruments, the Einstein Telescope Cosmic Explorer, I think will reach the sensitivity where for this pulsar, we can push the amplitude on this R mode down below what you would need. Okay, so it's a crazy idea, but it's testable. And I think all crazy ideas that can be ruled out by experiment should be put in print. Maybe.
Isn't that possible that it's actually masquerading like an error mode? It's just a completely different mechanism.
Oh yeah, yes, but it is very difficult to explain a breaking index of 7.
Okay.
You know, of course, you could say, look, maybe it's 6.75 and I just squinted a bit too much and I took that to be 7. I'll admit that's entirely possible. Right? But 6.75 would be, if I just made that up, but it would still be quite close to 7. So I would still have made that statement because it's a fair statement to make.
So did you already write, about this?
Yeah, the paper is out, and there are even some LIGO papers looking at, that system. So, which they would do anyway, because it's a regular glitching system. It's a young pulsar. Its spin is fairly nice, the LIGO sensitivity band. So they would look at this system anyway.
Okay, thanks a lot.
Yeah, thank you for the question.
So there are 2 more questions in the chat. The first one from, I can read them out just for everyone, from Julie Thomas, who suggests using quantum fluid experiments as a way to develop a fluid theory by averaging over vortices.
Okay, so I think that's a really good question, and I don't really know the answer either. Apart from, I think what one would have to do is find a middle ground, right? Where you have some way of, say, for a lab system, it's totally legit, I think, to do vortex line simulations and extract properties and so on. But for me, my system, I think, as I said, that's only ever going to tell me about one or a couple of fluid elements, right? And so one needs to figure out if there is some mesoscales of in between the lab system where I can write down a fluid model that performs well enough, that can then inform what I want to do. And so I think it's a discussion to be had. I think Julie's question is exactly to the point. I don't think you're missing anything at all, but there is discrepancy in scale where I have to work with fluid dynamics. For lab systems, you don't necessarily have to, right? Even though it's called two-fluid model. And so I need to be guided by something. And the only thing that can guide me are the lab systems. Otherwise, I'm a theorist roaming free, and I don't think anyone wants that.
And then just a final one about the deepinning mechanism.
Okay. So, the 2 pictures that we have is basically, one of them is that the accumulated Magnus force from a collection of vortices becomes too strong. So it just pushes them out. The pinning potential can't hold them. And so then the whole story is in what is the pinning force? And that's the word that Pierre Pizzichero did a lot of work on. Problem he was an expert on. The other possibility is that as you build up the fluid, the velocity lag, something kicks in, some instability that triggers, say, waves in the system, like in my picture, a two-fluid instability. You got two flows. The relative flow becomes large enough to trigger small waves, and these waves unpin the vortices because they shake them, right? So when you shake the vortices, they don't stay pinned anymore, and they go. I don't have a strong opinion either way. I think they're both viable, but neither of them are exactly calculable at the moment. So we need to do better.
Samuli.
Yes, I want to briefly comment on that. So in the polar phase, you never get vortex unpinning. Rather, what we believe happens is you get creation of anti-vortices, which then annihilate the vortices existing.
Okay.
And so in this sense, they never get unpinned. They can just disappear abruptly.
Right. So that's another thing, of course. If you have a mechanism for effectively vortex destruction, right? I haven't thought about that. I'm going to have to read your papers again because that's really interesting, I think. Thank you.
Okay, I think that's everyone. I'm about to be assaulted by a small child by the looks of things.
Excellent.
So that's where we can, she's held off. That's where we can finish for today. So just to advertise, the next talk in the series is on the 9th of May and is Laurent Chomaz from Heidelberg. But an email announcing that will come out in due course. Go on, trying to say hello.
Thank you, Andrew. Thank you, everyone, for putting up with me.
No, thanks very much, and thanks for persevering with your throat. Hopefully, it's not painful. At least
it sounds like I'm dying, right? But actually, it doesn't hurt. It's just bad. The vocal cords are just a bit messed up. So we'll see what happens. Anyway, thank you all.
Thanks, everyone. Bye-bye.